Hi everyone. Welcome to the stream. We'll wait for a few minutes as people will come in, but yeah. Today we'll be learning about polynomials. Hi everyone. Also, by the way, I probably won't see this in class, but just like as a beforehand note, if you guys want to like talk to me or like send messages to me, you can make a Twitch account, and that allows you to basically talk in the chat box on the right. So that way you can tell me your answers to the problems that we're discussing, or like if you have any questions, you can ask them. Yeah, if you're just coming in, we're just waiting a few minutes for more people to join. Uh, yeah, today we'll be going over polynomials. Yeah, so we'll be starting now. So basically, yeah. Also, thanks for Jonathan for like making the slides. So yeah, So for review, what is a polynomial? So polynomial is basically a sum of non-negative integer powers of variables multiplied by coefficients. So the non-negative integer powers part is especially important because this means that we can't have fractional variables. So like 1 over x in our polynomial, that makes it not a polynomial. If we have something like square root xy, as in the example on the screen, then that would not be a polynomial. However, x to the fifth plus 3x to the second plus 1 and the other example shown on the screen are polynomials because they have non-negative integer exponents. Alright. So polynomial division. So it's very much like regular division where you use the garage thing that you learn in like elementary school or middle school. But there are two techniques, long division and synthetic division. So first going over long division, we basically use the regular thing where we have a garage, which basically looks like a square root sign without the tail. So you basically eliminate the highest degree of the dividend one at a time, and since the polynomials have a finite degree, the division will always end. And since the quotient will also be a polynomial, if the divisor has degree n, the remainder will have a degree of at most n minus 1. I'll pause a bit as you guys take notes. Also, if you feel like I'm going too fast, you can go on the YouTube and you can like skip through and find parts that you struggled with when we upload the slides and YouTube recording. Alright, so for example, we have x to the fourth plus 3x squared plus 3x plus 1 divided by x squared plus 2. So I'll give you guys some time to work this out and try to divide it. And if you're struggling, we'll be going over a solution in the next slide. Also, feel free to ask any questions in the chat. Okay, so that should be enough time for you guys to have used division. So this is basically the solution. So we have x squared plus 2. So basically for this, we have x squared plus 2, and then we have x to the fourth plus 3x squared plus 3x plus 1 under the garage. So as you see, this like top left section of the square is like basically what I'm referring to as the garage. And above we have x squared plus 1, which is our solution. So as you can see, this is very similar to regular division with integers because we have the same technique using long division. So first we have x squared. So we multiply x squared and x squared plus 2, and then basically we subtract that from our dividend. Then we drop it down, and then we drop the next term down, and then we apply the same thing using 1 instead. So we do 1 times x squared plus 2, and then that basically leaves us with 3x minus 1 after we subtract. So basically our solution or our quotient is x squared plus 1, and our remainder is 3x minus 1. And also notice how our remainder is 1 less degree than our divisor. So our divisor is x squared plus 2, and our remainder is 3x minus 1. And 3x minus 1 has a degree of 1, whereas x squared plus 2 has a degree of 2. So that is in line with what we said about the remainder usually having 1 less degree or less of a degree than the divisor. Alright, so for synthetic division, this is basically a shorthand for long division, except only when we have a linear polynomial being our divisor with a leading coefficient of 1. So this is possible because each time you eliminate a term of degree n, you only change 2 terms. The term of degree n goes to 0, and the term of degree n minus 1 changes. So again, this is best shown by example, which we'll go through on the next slide. So our example is x cubed plus 3x squared plus 3x plus 1 divided by x plus 2. So basically, we see that on the left, we have negative 2, which is basically the opposite of the constant term of the divisor. And then we see to the right of the negative 2, we have 1, 3, 3, 1, which are the according coefficients of the polynomial that is being divided. So then the way that we utilize syntactic division is by dropping the first coefficient and then multiplying it by our constant term, the opposite of our constant term, which is negative 2. So 1 times negative 2 is negative 2, and we place it up 1 and right 1 in the next column. So that gives us 3 and then negative 2. Then we basically sum those values, giving us 1. And then we do the same operation of multiplying the negative 2 with the 1 and moving it up 1 and then right 1. So then we have 3 and negative 2 and then again. Then we add those again. And then we're left with 1 on the bottom. And then we do the same thing again, leaving us with all 1, 1, 1, 1 on the bottom. So basically what this means is that our quotient is x squared plus x plus 1 with a remainder of 1. So basically, the reason why our quotient has shifted a degree downwards, that's basically just how syntactic division works, but also that's something that we discussed before in the previous slides. That should be taken by note. A note should be taken, yeah. Also notice how the right-handmost number on the bottom is basically our remainder. Alright, so for practice, let's do these problems on the slide where we have to use both synthetic and long division in order to calculate the quotient. Also, make sure you follow, if you take notes, make sure you follow the steps that we discussed earlier in the previous examples with synthetic and long division. I'll give you guys a few minutes to solve these two. If you're struggling, feel free to ask in the chat box. If you don't have a Twitch account, you can make one easily with just your email and just creating a password. Okay, now should have been enough time to solve these problems. So the solution to 1 is x squared plus 2x plus 1, and the solution to 2 is x squared plus 3, and the solution to 3 is x plus 5. Hopefully you guys all did fine on that short exam. Alright, so using polynomial division, we basically get the remainder theorem. So if we divide the polynomial g of x if we divide any polynomial by another polynomial, we get a polynomial as a quotient and another polynomial as a remainder. So we can write this out as g of x, which is our polynomial that's getting divided, h of x, which is the dividing polynomial, times q of x, which is our quotient, plus r of x, which is our remainder. So this is basically like a regular integer remainder representation, So if we have like a number of 9, which would act as like g of x in this case, and we had 7 as h of x, we can basically use the same type of model in order to have q of x as 1 and r of x as 2. So basically when we divide 9 by 2, we get the remainder of 2. 9 by 7, we get a remainder of 2. So this is a very similar model to how we would represent regular remainders in integers. So using this model, the remainder theorem states that if r is a root of h of x, then g of r equals r of r. So basically this is clear since if x equals r, then h of x would be 0, and anything times 0 is equal to 0. And that basically leaves us with g of r equals r of r. Also remember that when r of x is a polynomial, remember that this is when r of x is a polynomial, but there's also a special case when r of x is a constant. And we'll be discussing that in the next class. Next slide. Alright, so to continue, we'll be discussing when r of x is a constant. So we'll notice that when we're dividing by a linear equation, a linear polynomial, or basically a polynomial with degree 1, or in the form of x minus r, then r of x has degree 0 no matter what, which means that it will always be constant. So basically when we have g of x divided by h of x, so basically we can say that when g of x is divided by h of x, then the remainder is g of r, using the remainder theorem basically. But notice that this is only when h of x is a linear polynomial. Also, we can even say this if r of x is not constant. For example, if r of x was not constant, then g of r would be r of r. So we could have g of r equals to 3, but that does not mean that r of x equals 3, but r of r would equal 3 after we substitute x. So we'll be going over a problem. So basically, solve this problem that states that, so basically you want to find a remainder of x of 9 to the 99th power minus 9 times x to the 97th power plus x squared plus 1 when it's divided by x squared minus 4x plus 3. And don't try to do long division because this will take a long time. And also, you can do this with a calculator, but don't do it because this is good practice for the remainder theorem. Yeah, and again, I'll be giving you some time to solve this problem. Again, if you have any questions about this problem, feel free to ask in the chat. And also, if you just have an email, you can basically make an account. So there's no reason not to if you have a question. Okay. So basically the solution is that, so we basically know that the roots of the divisor, x squared minus 4x plus 3, is x equals 1 and x equals 3. So we define the remainder as r of x, and then define the dividend as g of x, knowing that r1 equals g of 1 equals negative 6, and r3 and g3 equals 10, we can basically solve for the coefficients of a linear equation, since we know that since the divisor has a degree of 2, we know that the remainder has at most a degree of 1. So basically we solve mx plus b, where we substitute x as 1 and 3. So we just basically solve m and b, where m plus b equals negative 6 and 3m plus b equals 10. And after solving this, we get the remainder polynomial is 8x minus 14. Also, by the way, we know that g of 1 and r of 1 equals negative 6 because we can substitute that into our original polynomial, which is the x to the 100 minus 9 of x to the 98 and all that stuff. So that's how we know that r of 1 and g of 1 equals -6 and r of 3 and g of 3 equals 10. Alright, so then we're discussing the factor theorem, which is basically a special case of the remainder theorem where r of x, which is basically our remainder polynomial, equals 0. So after we know that the remainder is equal to 0, we basically have that g of x is a factor of f of x. Or that g of x, which is the dividing polynomial, is a factor of the polynomial getting divided. And this is very similar to regular integer remainders. So if we have 81 divided by 9, the remainder is 0, so therefore we know that 9 is a factor of 81. So now let's go over a problem where we have to show that x to the 1000 plus x to the 998 plus x to the 4th minus 3 can be factored into x squared minus 1 times f of x, where f of x is any polynomial in x. And again, I'll be giving you guys some time to solve this. And if you have any questions, feel free to ask in the chat. Okay, so it should have been enough time to solve this problem. So basically, all we have to show is that x squared minus 1 is a factor of g of x, which I won't say the whole polynomial, but yeah. So basically, looking through the polynomial, we can see that 1 and negative 1 are both roots of the equation. So multiplying these together, it gives us x squared minus 1, which is a factor. So after we multiply it together, we get x squared minus 1, and that shows that x squared minus 1 is a factor of g of x. Because for any polynomial, for like x minus 3 times x minus 4, we can basically represent it by its roots as I just did. So by using this and multiplying them together to get x squared minus 1, we basically get that x squared minus 1 is a factor of g of x. So now let's go over the rational root theorem, which basically gives us information on which rational numbers can possibly be roots to a polynomial. So considering this polynomial with coefficient terms and powers of n and n minus 1 all the way to 0, with coefficients that are integers, the rational root theorem states that the only possible rational roots are in the form of a of b over b, where a is a factor of the constant term and b is a factor of the leading coefficient. So if we had a leading coefficient or a constant term of, say, 9, our a can be 9, negative 9, 3, negative 3, 1, and negative 1. So when our constant term and leading coefficient have a lot of factors, this may be a bit bashy, but otherwise it's a useful method. Right, so to basically prove this, we assume that p over q is a solution to our polynomial that was in the previous slide, and we assume that it's a fully simplified fraction. So by substituting into the polynomial and multiplying both sides by q to the n, we get that new polynomial as shown on the slide. So since the right side of the equation is 0, which is always a multiple of q for any q, the left side must also be a multiple of q. Since every term is a multiple of q except the leftmost, because p over q is fully simplified, they do not share any factors, so the leading coefficient must be a multiple of q. And also, with the same idea, the constant term must also be a multiple of p. So for example, we want to find a rational root to x to the third plus 4x squared plus 7x plus 4. So writing out all forms of a over b, So basically all factors of 4 over all factors of 1, we get the possible roots of plus or minus 4, plus or minus 2, and plus or minus 1. So then we just use synthetic division to quickly trial our options. And then after we do that, we basically get that our answer and our rational root is -1. Note that by using synthetic division, we also get the quotient after we divide by x minus 1 or x plus 1. So to practice, find the real roots of 2x to the fourth plus x cubed plus x squared plus x minus 1. Additionally, using the rational roots theorem, determine the possible rational roots of 5x to the third minus 7x squared plus 8. Okay, I'll give you guys a few minutes as well. Okay, so let's go over the solution. So basically, for the first problem, the possible rational roots using the rational roots theorem is plus or minus 1 and plus or minus 1/2. And using synthetic division, we basically try out each of our possible rational roots, and we find that -1 works. And using that, we get that x plus 1 as dividing our original polynomial gives us 2x cubed minus x squared plus 2x minus 1. Also note that 1/2 also works, but by synthetic division, 2x cubed minus x squared plus 2x minus 1 divided by x minus 1/2 gives us 2x squared plus 2. Because that does not have any real roots, only complex ones. The real roots of the original polynomial are -1 and 1/2. Also, we might be discussing complex numbers in maybe a future class, so feel free to just note it and move on if you don't understand what that means. And also to briefly go over problem 2, the possible rational roots, we basically just directly apply the rational roots theorem. So we have the constant term of 8 and the leading coefficient of 5. So we have plus or minus 8/5, plus or minus 4/5, plus or minus 2/5, plus or minus 1/5. And we also have plus or minus 8, plus or minus 4, plus or minus 2, and plus or minus 1 by directly applying the rational roots theorem. So finally, thanks to all of you guys watching. This is the slide we just went over. This one was the final slide of our presentation. But if you'd like to keep in contact with us, feel free to join our Discord and also check out our website. And if you want to check out our other lectures or go over this lecture again, feel free to check out our YouTube. And also, all the presentations and an additional problem set will be posted in our Discord and on our website. So if you'd like some additional practice or you want to maybe learn more, feel free to join the Discord and check out our website, which is focuslearning.github.io/nothing else, because yeah. So that's it. Thank you guys all of you guys for attending, and have a great night.